We're now going to look at the calculus of parametric functions. And so if you still aren't really comfortable with parametric functions, I encourage you to stop the video right now and just go back and review parametric functions on your own. I will go ahead and link some of my video lessons on parametric functions in the description box below. So go ahead and check those out if you need to. But once you have a baseline understanding of how parametric functions work, we can go ahead and resume this lesson. So today we're going to talk about the calculus of parametric functions, and we're going to start by looking at the derivatives of parametric equations. Now, again, if you remember what a parametric equation is, they are simply equations written with respect to some parameter. So we can say that x, for example, is a function of some parameter t. And we can also say that y is a function of some other function of t. And these parametric equations give us really valuable information, and they typically actually behave much better than the rectangular form of this equation. And so when we're finding the derivatives of x and g, which is equivalent to finding the derivative of the derivative of x and y, that typically isn't too bad. However, if we want to get valuable information from our derivatives, we still need to know the slopes in the plane, or in other words, we need to find dy dx. We need to find the rate of change of our y, which is a parametric function of t. We need to find the rate of change of y with respect to x, which means we need to find the rate of change. What that means is what we're going to need to do is we're going to need to find the rate of change of y with respect to t, and then we're going to need to divide it by the rate of change of x with respect to t. Now, why are we doing that? Why do we have to find the rate of change of each of those and divide? Well, the answer is it really comes down to the chain rule. If we say again that we know that dy dt, for example, can be written as the following. It's the rate of change of y, so it's the rate of change of y with respect to x times the derivative of x with respect to t, dx dt. This is just the chain rule here. Well, you can see here now the dx's would divide out, and so we get the equivalent sides. However, if I want to go ahead and I want to isolate dy dx, if I want to get that by itself, well, what does that mean? I'm going to go ahead and divide both sides by dx dt. And I'm sorry for the sloppiness right here, dx dt. I'm just going to write over this just temporarily. But what that allows me to do is it allows me to write the following, that dy dx, and I'll just rewrite it cleanly here, dy dx is dy dt over dx dt. Okay, so I'm going to just kind of clear this out here just so we can hopefully see that. So just go ahead and write that there. So what we're again saying is the following. If we want to find the rate of change of y with respect to x, given that y and x are both parametric equations, they are both parametric functions of t, we first need to find the derivative of y with respect to t, and then divide it by the derivative of x with respect to t. We can't see how y is changing with respect to x unless we understand how x is changing with respect to t, right? Remember, it's really just another way of thinking about the chain rule here. So that's going to be really important because when we're looking at the second derivative here, oftentimes when students are finding the second derivative of parametric functions, they'll just go ahead and find the derivative of, again, of dy dx. But if we remember again that when setting up our understanding of finding derivatives of parametric functions, we have to make sure that we understand to find d2y over dx squared, right? Or the second derivative, we need to first find the derivative of dy dx. So we're going to differentiate dy dx, whatever we got as our first derivative. But then we also, again, have to divide by dx dt. And just to reiterate, to find the rate of change of something with respect to x means we have to find the rate of change of that something with respect to t and divide it by the rate of change of whatever your inner function dx, in this case x, with respect to t. So really just keep that in mind as we go through the second derivative. Okay, that is the rate of change of something with respect to t divided by the rate of change of the other function, x, with respect to t. So let's do an example, and I think hopefully that'll help this make a little bit more sense here. Let's find both the slope and the concavity of x is equal to root t and y is equal to 1/4 t squared minus 1. Notice I'm also giving you an interval for t, because both x and y are parametric equations. I need to give you some type of interval for t so we know where we need to be looking. And that slope and concavity is going to be determined at the point 2, 3. So since I'm finding the slope, I know I'm going to need to find my first derivative. And since I know I'm finding my concavity, I'm eventually going to need to also find my second derivative. Let's start by finding the derivative of x and y with respect to t. So we can say dx dt. Let me just zoom on this a little bit more. Dx dt is just the derivative of x. So again, this part isn't too bad. So the derivative of root t is just going to be 1 over 2 root t. Now let's find the derivative of y with respect to t. So dy dt is just going to be 2 times 1/4, so 1/2 t, and the derivative of -1 is just 0. So that's the derivative of x and y, both of these with respect to t. We're going to use these now to find dy dx. Okay, and this is going to allow us to find our slope. And let me just highlight that here so we know exactly what part we're finding to find our slope. This is going to be dy dt over dx dt. So I can say 1/2 t or 1/2 t or t over 2, doesn't matter, all over 1 over 2 root t. Well, this can be rewritten as t over 2 times 2 root t. So when we're dividing by a fraction, it's just multiplying by the reciprocal. And when we clean that up, that's just going to give me t to the 3/2 power. Okay, so that's going to be our slope, dy dx. And we can use that, again, to evaluate the slope at any given point. All right, so I'm just going to move that over just so we have a little more space to work with. All right, now let's go ahead and let's find, actually, let's finish up finding the slope. So since we know this, since we know dy dx, we can use it to find the slope. So the slope is going to be dy dx evaluated at the point 2, 3. So what we're going to do is we're going to evaluate t to the 3/2 at the point 2, 3. Now, the problem, however, is that we've got a function in terms of t, but we're evaluating it using our x and y. Well, the quick solution here is we just need to find out what is t when x and y are equal to 2, 3. And we're going to use our parametric equations for that. So when x is equal to 2, and it doesn't really matter which one you use, okay? So when x is equal to 2, right? We're using this coordinate here. When x is equal to 2, what is t? So let's plug it in using this equation here. So when x is equal to 2, 2 is equal to root t, which means that t then is equal to 4. So when your xy value is 2, 3, because this, again, for the rectangular equation, when x is equal to 2, y has to just be one other value. So it doesn't matter which one you use. So when x is equal to 2, we can say that t is equal to 4. So now we can evaluate our slope at the t value 4. And when we plug 4 into this, we should just get 8. So what we just found is our slope at the point 2, 3. Now, let's go ahead and let's find the concavity. So I'm going to leave that there, but let's move on over to finding our concavity. So again, our concavity now is going to be our second derivative. So let's find that. What is our second derivative? Now, again, before you just go ahead and differentiate our first derivative, right? Although we will need to do that. So the derivative of our first derivative, t to the 3/2 power, is going to be 3/2 t to the 1/2, or t 3/2. So let me write it like this. Well, actually, I'll leave it as t to the 1/2. Okay, so that's the derivative of our first derivative. However, don't stop there. We then need to divide that by the derivative, by dx dt again. Okay, and what is dx dt? It was 1 over 2 root t. 1 over 2 root t. And actually, let me just go ahead and leave that as root t here. So to clean this up, what do we have? We have 3/2 root t. When we divide something by, when we divide by a fraction, it's multiplying by the reciprocal, so 2 root t over 1. And that allows me to then say that's just going to be 3t. Now, again, we need to evaluate to find our concavity at a specific point. We're going to evaluate it at the point 2, 3, which we've already established that t is equal to 4 when that happens. So this evaluated at t is equal to 4, 3 times 4 is just going to give me 12. So if our concavity is equal to 12, it is greater than 0. Therefore, it is concave up at that point. So what we can now do, and you may want to just do this on your own real quick, is to put those parametric equations into your graphing calculator and look at the point 2, 3 and see, would it look like we have a tangent line there with a slope of 8, or that the slope there would be 8, and is it concave up at that point? And both of those should be true because I said so. Just kidding, because we just did this problem here, okay? All right, I'm gonna go ahead and try one more problem here for this part, and then I'm gonna let you try number 3 on your own. And again, you can always check your solutions with what I have uploaded in my classroom. But for number 2 here, let's go ahead and try this one. Now let's actually go through the exciting challenge of writing an equation of a tangent line to the curve of this parametric set of parametric equations at the point when t is equal to 1. So these two parametric equations are going to give me a plane curve, and when t is equal to 1, I want to be able to write the equation of that tangent line. All right, so let's find, starting with dx dt. So we know what x is, so dx dt is simply going to be equal to 1. Now dy dt is going to be, let's see, the derivative of 1 over t is going to be negative 1 over t squared, okay? So now, let's now put this, when t is equal to 1, let's establish a couple of things here. So when t is equal to 1, well, actually, you know what? Well, might as well finish this. When t is equal to 1, we know we're going to need some x and y values for our tangent line. So let's just do some evaluating. When t is equal to 1, excuse me, when t is equal to 1, what is x of 1? Well, that's just going to be equal to 0. When t is equal to 1, so y of 1 is going to be 1 over 1 plus 1, and that's equal to 2. Okay? And so we know from this information that our point, our x and y coordinate, our rectangular coordinate is 0, 2. So that is the coordinate that our plane curve is going to cross through when t is equal to 1. Next, let's finish finding our slope. We found our dx dt and our dy dt. So now let's find dy dx. And we know we're going to need to evaluate this at t is equal to 1. So dy dx is going to be dy dt over dx dt. So in other words, negative t, let's write this, negative t to the negative 2. All of this over, well, dx dt is just 1. So if I evaluate all of this at t is equal to 1, this makes it pretty easy to calculate. So we plug 1 into our derivative, and we're just going to get negative 1. And this here is our slope. Okay? Now that we have that, I think we're ready to put it all together. So let me just switch on over to my final color. So let's put it all together. We know that our tangent line is y equals y1. Y minus y1 is equal to m times x minus x1. Our coordinate, y minus 2, again, we chose that. Our slope was negative 1, x minus 0. And as you'll often hear me say, unless it tells you to simplify, you don't need to, right? Decrease the chance that you might accidentally simplify something incorrectly. And so now we were able to find the equation of a tangent line for this plane curve given from the set of parametric equations.